Hello everyone. Now let us discuss the next module of digital communication. In this module, we can discuss the differentially encoded PSK. In the last module, we have completed the DPSK, which is a non-coherent version of binary phase shift keying. Now let us discuss the differentially encoded PSK. So here you can see that this differentially encoded PSK, it is a combination of DPSK transmitter and BPSK receiver. We know the advantages of differential phase shift keying transmitter because it consists of differential encoder and product modulator. The circuit is very simple, as well as here the bandwidth required for transmitting the DPSK signal is half to that of BPSK. So that's why we have chosen DPSK transmitter, and because of coherent detection, we have taken BPSK. So coherent detection will reduce the probability of error and improve the SNR. So differentially encoded PSK provides the advantages of both the DPSK transmitter as well as the coherent detection of BPSK. So like that we have a lot of advantages for DEPSK. Here, the similar to the DPSK, here the phase change is only for 1 bit data. For example, if you are using XOR gate, then it is only for the data bit 1. The DK is the complement of DK minus 1. Other than that, there is no phase change. Okay. Next, we can discuss the and coming to the bandwidth, as I already said, the bandwidth is FB because the bandwidth for MRAPSK is 2FB by N. 2FB by N. Here N is 2. So that's why the bandwidth will be FB, which is half to that of BPSK. So that is the advantage of DEPSK, similar to DPSK. And already we discussed that the modulator is same as DPSK. So like that here we have taken the differential encoder and XOR gate is taken, which will compare the present binary bit with the past differentially encoded data bit, that is DK-1. Then BK and DK-1 are compared to produce the differentially and current differential data bit. Now that data sequence is multiplied with a carrier to produce the DEPSK signal, which is in the form of DK AC cos omega CT. This is our DEPSK transmitter, which is same as DPSK, which consists of differential encoder followed by balancer modulator. This balancer modulator is nothing but which takes the product of uh, bipolar ratchet, which is the differential encoder output with carrier. So ultimately, we can see that this is same. This data is same as the DPSK signal. Now, let us see the transition. For example, we already know that the differential encoder inputs are BK and DK-1, where BK is the binary data and DK-1 is the past differentially encoded data. For example, if BK is equal to DK-1, that may be 0, or 1, combination. Then you can see that the differential encoder output is 0 with a phase change of 0 degrees. For example, if because we have two inputs, 4 combinations there. If there is a transition, that is, if both the for unidentical inputs, 0, 1 or 1, 0 combination, if you see, the differential encoder output is 1 with a phase change of 5 radians or 180 degrees. And another thing that you can observe is that here when BK is equal to 0, that is when binary data is 0, you can see DK-1, that is 0 and 1. That is 0 and 1. For 0 and 1, DK-1, we obtained DK as 0 and 1. That is, when the binary data bit is 0, there is no difference between DK and DK-1. Both are same. For example, if BK is 1, then you can see DK-1 is 1, 0, and but DK is 0, 1. That is, DK is a complement of DK-1 when BK is 1. Now let us see the basic truth table. Here you are taking binary data bit in XOR with dk minus 1 to produce dk. So we know that for same inputs, for identical inputs 0 and 0, the output is 0. And similarly for unidentical inputs, the output is 1. These two are the unidentical input case, that is 1 and 0 or 0 and 1. You can see the outputs as 1 only. And for identical inputs, that is for 0, 0 or 1, 1, the output is 0. And now, another thing is that in the last previous slide, we have seen that when bk is equal to 1, we obtained dk as a complement of dk minus 1. But when bk is equal to 0, we obtained dk as same as dk minus 1. The same here we represented. When bk is 0, dk is same as dk minus 1. But when bk is 1, we can see that dk is a complement of dk minus 1. Here dk minus 1 is 0, so but we obtained dk minus 1, dk as 1. That is complement of dk is a complement of dk minus 1 in this case. Similarly, here also dk is a complement, and here also dk is a complement. Like that, you can conclude. Next, let us see the DEPSK receiver. In this receiver, we already discussed that it is a combination of BPSK receiver and followed by the only extra element added is XOR gate. Here, if you see the coherent carrier, this coherent carrier generation consists of 3 blocks: square law device, band pass filter, and frequency divider by 2. The input here is the noisy BPSK signal. Sorry, this is differentially encoded PSK. In this differentially encoded PSK, the general form is dk into AC cos omega ct. Here, let us introduce theta as a phase variation. Now by using these 3 blocks, we have generated the coherent carrier, and here you are using a multiplier which takes the product of DEPSK and coherent carrier. The product is applied to the integrator, and along with that, the multiplier output is applied to the bit synchronizer for timing synchronization. And here you are using 2 switches. This procedure is same as BPSK. If you have any doubts, you can go through that lecture. And here switch S1. Switch S1 is closed at time interval 0. And from 0 to bit intervals TB, both switches are made open. Once both switches are made open, integration of this is performed. So you will get ramp signal. And after completion of the bit interval, switch S2 will be closed. Then the integrator output is applied to the decision device. These timing intervals are provided by the bit synchronizer, and frequency or phase synchronization is provided by the coherent carrier generation. And now the low pass filter output is applied to the reference voltage. If the low pass filter output is greater than reference voltage, the decision device output is 1. If the low pass filter output is less than reference voltage, the output is 0. Now finally we obtained the decision device output, let it be D suffix k. Take 1 bit right shift of this dk and compare it with take XOR, because at the transmitter in DPSK we have XOR gate as a differential encoder. So you are using differential decoder as a receiver. Again, so we are using same XOR gate. This XOR gate compares the dk and dk minus 1 to produce the binary sequence dk. Here also we will use the same procedure, that for identical inputs, that is when dk is equal to dk minus 1, output is like a 0. When dk is the complement of dk minus 1, output is 1. Now let us, we already discussed that a phase lock should satisfy frequency and phase synchronization as well as timing synchronization. We already discussed this concept in BPSK, because DEPSK is the same DEPSK receiver is same as BPSK receiver. So we know that DEPSK signal is in the form of dk AC cos omega ct plus theta with a phase deviation of theta. And if you take the square law output, it is cos square x. So you can write it as 1 plus cos 2x by 2. Once it is allowed through the band pass filter, the band pass filter does not allow the DC component. So this DC component is not allowed. So you will get only the cos 2 omega ct plus theta. Once it is applied to the frequency divider by 2, you will get cos omega ct plus theta as the carrier. So multiplier, again we have multiplier which multiplies the DEPSK signal with synchronous carrier. Upon multiplication you will get dk into AC cos square omega ct plus theta. And we have written AC as root 2ps, and this is in the form of cos square x. We can write it as 1 plus cos 2x by 2. And once it is applied to the low pass filter doesn't allow the higher frequencies. So only the DC component will be allowed. So output will be dk into root 2ps into dB at respective interval. So low pass filter output now is compared with the decision reference voltage in the decision device, and decision device output can be 1 or 0 when low pass filter output is greater than reference voltage or less than or equal to reference voltage. This whole thing we discussed in the BPSK module. And now from this, from decision device, we will apply the output to the XOR gate. And this is called as differential decoder section, consisting of XOR gate having the inputs as dk and dk minus 1, where dk minus 1 is a 1-bit right shifted sequence of dk. When both are same, output data bit is 0. When both are different, the demodulated output is 1. But the only drawback in DEPSK is that in DPSK we have already seen that if there is any 1-bit error, the bit error gets propagated. But here the bit, for example, if you have 1-bit error, it affects 2 bits in the output. Let us see. In the left side, you can see that the transmitter principal. This is the transmitter principal. dk is equal to bk XOR dk minus 1. That is differential encoded data is this is the output of differential encoder at the transmitter. dk is equal to bk binary data, that is the upcoming message, XOR past differential encoded data. And at the receiver we are using differential decoder, where the demodulated output bk is equal to differential encoded data XOR with 1-bit right shifted differential encoder. Let us see the principle of receiver. We know that bk is equal to dk XOR with dk minus 1. Let us see the sequence as 0, 1, 1, 0, 1, 1, 0. Take the 1-bit right shift. So if you take 1 bit, all the bits get shifted to towards right side 1 by 1 bit. So the last data bit 0 comes as a out of alignment. So we can remove this. So you will have 0, 1, 1, 0, 1, 1, 0, and this 0 is a leftover bit if you do 1-bit right shift. Now let us take the XOR of all the bits. So 0, 0, it is 0. Similarly 0, 1, you can see the output is 1 because different inputs. Similarly for same inputs output is 0, different inputs output is 1. Like that for same input again 0, for different inputs output is 1. Like that you obtained binary sequence. This is error free signal. Now we are introducing 1-bit error. Instead of 0 here at the 4th position, we are introducing 1. So again for testing, take 1-bit right shift. So take 1-bit right shift and this will be out of alignment. Again do the XOR operation. If you do the XOR operation 0, 0, output will be 0, different data 1, same data 0, again same data 0, same data 0, same data 0, different data 1. So here if you observe, we are introducing only 1-bit error, but it is affecting 2 bits at the output. So in DEPSK, it may not get propagated, but if there is any single bit error, it affects 2 bits at the receiver. And already we discussed the bandwidth, it is equal to of DEPSK equal to FP. Though the advantages are already we discussed, the bandwidth is half to that of BPSK, that is one advantage. And we are using coherent receiver because BPSK receiver is used here. So the probability of error is less. So SNR is high. Similarly, the phase of carrier similar to DPSK, here also the phase of carrier changes only for data bit 1. But in BPSK, phase of carrier changes for both the data bits 1 to 0 transition or for 0 to 1 transition. And here the implementation of DEPSK system is complex. And again, another thing is here error bits may not get propagated throughout the entire sequence similar to DPSK, but here single bit error may affect 2 bits in the output. So DPSK error occur in pairs. This is due to the nature of differential encoding and decoding process. The applications remain same as that of BPSK and DPSK. So in this module, we have completed the DEPSK transmitter and receiver sections. In the next module, we can discuss the concept of uh, binary frequency shift keying. Thank you for listening.